Hey. Okay, well, I'd like to express my gratitude for every one of you who attended today, and thanks for making effort to come. And I hope you are going to witness the very early beginning of the space-time or synchronization effort in Japan today. And it's really my great pleasure to introduce Ahmad Byagowi to you. And Ahmad is a research scientist focused on time and frequency synchronization in hyperscale networks. And Ahmad received his first PhD from Vienna University of Technology working on distributed control systems in 2010. So there is already a hint about the importance of synchronization there. And following that, Ahmad went to the University of Manitoba, and initially as a postdoc fellow, working on game engines and virtual reality systems. Due to his interest in the project, he started a second PhD and finished in 2016. And after that, he started working with Professor Ramesh Raskar from the MIT Media Lab on haptic systems. This led him to Facebook as a visiting scholar, and he was impressed by the research there and decided to join Facebook, now Meta, in 2017. Ahmad, floor is yours.
Thank you. Thank you very much, Nobu, for one introduction, and thank you for having me here. And so today's presentation will be about precision time synchronization between end users and also data centers. So I'll try to have a balance between explaining how and why basically we do this synchronization. So the motivation is let's say we can break it into two sections. One about the synchronization between end users, and the laptops or cell phones, you name it. And then the second one will be mainly about what you do with it in a data center, the provider basically. And so let's start with the end user. So one thing that I witnessed is always challenging when you go with multi-users and you're trying to get, let's say, multi-users to cooperate, whether it's a game or they're working together and so on, is the latency. And in this chart, what you see is basically this user trying to interact with this user on the right, and then the data has to go through latency, inevitably, some latency is there. And then if you just have some simple, basically state-of-the-art today's work, you are projecting where the user was rather than where the user is. So to human perception, let's say if things are with, let's say, less than 50 nanosecond, 50 millisecond, right? That'll be still not perceivable. Let's say, as there's entire research on that. As latency increases, let's say you get to 100 millisecond, 1/10 of a second, then things start you start to realize, and then let's say when it gets to let's say 0.2, 0.3, 0.4, then it starts actually becoming annoying and you cannot actually use it anymore. So what can we do with this? So we can break it down to see what is the source for latency. So part of it is, let's say, for example, speed of light. At least for the foreseeable future, we probably cannot go through this. That's speed of causality. Transceivers are getting better, and that's basically, let's say, when you have optics or something, and you have queuing and buffering. That can also get better if we, let's say, utilize time and, let's say, have smarter queuing. You have QoS, quality of service. And then also you have things that are on the end user, like the peripherals and like the OSI model, and then how data basically propagates and so on. All in all, latency will degrade the user experience. The user experience that needs to create an illusion of defying distance. You're talking to another person in virtual reality that is, let's say, thousands of kilometers away, and you're trying, and the same, you are away to that person, and the system is trying to make the illusion that we call it like illusion of presence, that the other person is right in front of you. But then when you do the interaction and they take long, then you will lose that immersion. Then this is not like, it's not going to give you basically that effect that you're looking for, that is basically defying distance. So what can we do? There are certain things we can eliminate, but if you cannot eliminate something, you should manage it. And managing latency means you have to precisely measure it, and if you can precisely measure latency, you can do estimation and projection. Meaning, let's say with generative AI, and then you have, let's say, avatars, you don't have to show where the person was, you can show where the person is by measuring, let's say, successions of how the motion was going through. And again, it's not going to respond to spontaneous things, but let's say, if let's say two parties are playing, let's say ping pong or something, and someone's hand is moving, you are measuring precisely all the timing for where, let's say, the hand was in, let's say, last steps of 10 milliseconds. So then you can project by knowing also that the latency is like another 40, 50 milliseconds, where this is going to be shown as it's going through. So this is basically a process of prediction and compensation. And again, all of these can be possible if you have precision in your measurement. And in this case, for latency, is precision time. So now we can take a deeper look at like the whole chain from the cloud all the way to the user, and how far are we in terms of technology, and what are the things that are missing. A spoiler, most of these things are already available. We just need to put them together. So to start with, if you have 5G already, most of the 5G implementation, they already have precision time. So but the thing is, like, the precision time is mainly on the tower to do basically that handover, or you name it. All you need to do is basically, again, if the need is there on the end user, you can have those hooks, and now you can get the time basically on the end user. When it goes to the end user itself, you're entering in a system. Of course, data is coming from the NIC, Network Interface Controller, all the way to the OS, let's say, right? And then from the OS, again, you have like different peripherals, and again, this depends, like if you have, let's say, keyboard and mouse and a monitor and everything. All these pieces today, they are relying on basically the software interaction, and let's say the PCIe bus, let's say, connecting to GPU, connecting to USB controller into the peripherals. All of these devices are capable to do precision time with technology like PTM. And even like on the software layer, a lot of advancements have been like done to make sure time, like basically you should look at this. It's very interesting that how a network like NIC is no longer just data, is also time, providing you time. So as most of you are familiar, let's say with PTP, precision time is actually on the NIC. And now from the NIC, you can basically have, like, let's say, if you want to take like the software route and go through, like, let's say, the OSI model, of course you will lose a lot of precision. But again, thanks to some newer technologies, you can actually bridge this too. So, as I mentioned, PTM stands for precision time measurement, allows you to do that. And how it does it is basically now you have hardware timestamping on the PCIe data exchange, and now you can associate the time that was on the PHC of the NIC with the time that is on the CPU, on always running timer. And now from there you can actually go backwards, and now you can have, let's say, your GPU also in sync. You can have the peripherals now in sync. So this, again, going back to that first part, now the system can propagate the time, let's say, as long as it arrives to the NIC. Now, this is not just theoretic. We actually have this. Like Intel has any CPU that is 11 Gen Plus, and the latest Xeon processor can do this. So we actually have this prototype, and then we are showing, like on the scope, let's say, the synchronization. Again, between these two NUCs, we have PTP running. There is a like the PPS output for the two NICs, so you can see it here, from here to there. And then from every one of these NUCs, the CPU can also give a PPS signal, so you can compare the two, like basically end to end. And Satoshi has a sample in NICT. So, and this is basically over time, like with just some latency, and you see like the error is like, again, this is the reference, and you like to call it leader, so leader and follower, right? We call it usually server and client. So that's the terminology we use. So this is basically the server, and this is the client. This is for PTP. And then the same machine going from that NIC to the CPU is this, and then from that NIC also to the other CPU. You see, like the precision is less than PTP, of course, because again, it can get improved. Right now, the granularity is only 4 nanoseconds. For the Xeon, it's 2 nanoseconds. So now, moving forward, let's say you have the time in the NIC, but how can you synchronize that machine? Well, simple. Put a GPS on the machine and ask everyone to work outside. Is that possible? Well, not so good, right? So, and so you need to have some more, let's say, thoughts to make something, work, not necessarily just outside. So with some of my colleagues, notably Julian, so we actually, I don't know if you're familiar with the time card, we made the time card also much smaller and got 2 form factors. So now you can put it actually in your computer that you're supposed to use only outside. But luckily we have friends in NICT, and again, I don't want to spoil the slide for it, that you don't have to go outside. You can have synchronization inside. So the second part is, well, we don't want to put GPS antenna on the end user. Let's put the GPS antenna on the router. So if you put the GPS antenna on the router, again, these are different parts. Let's say on the router you have like, I don't know how it's in Japan, let's say the connections for the, what you have with the ISP, but we'll go through it and see like how much similarities we have. Let's say if you have that, then you need a GPS antenna for every, let's say, building, and then you put on the main router a GPS receiver. GPS receiver feeds into the router, and then you still have a problem how to get basically from the router to all the devices, unless they're connected with Ethernet, so then you can do PTP. But if you are doing wireless, then the solution is a little bit more tricky. But luckily, with the work, again, we'll have an entire slide about that. With the work from NICT and YY, you can perhaps take care of this part. And this slide you see is like before I met Nobu in last year OCP. So now, so in this case, you see like the point where timing comes in is the router in your house. And then from there, you have like the synchronization of the system. And then once you get the system, but this is the NIC. Basically, you go with PTN. All of the rest are necessary. You can do the PTN to the end user, you get all the way to the CPU, and you can do a lot of different things. So, again, then shows up Nobu in OCP and pretty much brings a great solution that we can do now, synchronization in wireless. And that was a great, let's say, solution that will fit basically in this whole ecosystem. We'll get to it in a moment. So now let's say, aside from you want to go with wire or wireless from there, going one step further, let's say you don't want to have in every house. Let's say it's possible if you are like living in a single house, like single family house somewhere, and you have access to the roof or something, still a little challenging. But let's say in an apartment complex or urban life, you can't have a GPS receiver for every house. So you're looking for a little bit higher in the hierarchy, which you can look perhaps for the modem and to the ISP server, the internet service provider. In the US, we have usually DOCSIS, or also 5G. I don't know again what's in Japan, but I'm assuming it should be similar. So DOCSIS itself, very interestingly, has in chapter 6, it describes actually the ability to do 1588. So the hardware is already there, but it's not used. Hardware is there, from what I understood, is it's to synchronize these like the TV boxes to do the scheduling right, or I don't know, the video that they want to show, they want to make sure it's like the latency is managed and so on, but it has never been used as far as I know. And so easily this can be, like, let's say, synchronized with something higher, or let's say the ISP, the internet service provider, can have like the GPS receiver, and from there you can go to the router in the house, and then from the router in the house you go again YY, or let's say if it's Ethernet with PTP to the end user, and then the end user PTN, you go to the CPU. Now, let's say the internet service provider will have a challenge, let's say with GPS or something. Then again, this is if the internet service provider has a GPS, you can basically go to the DOCSIS and get things in. In case of 5G, as I mentioned, the towers, they're already in sync, and you can actually reverse the process by looking at a certain point in the like in the LTE frame, for example, in case of LTE. You look at a certain point in the framework where like in the frame, that you have actually the time, and you can take it from there. This work has been done by NXP, and there are also some other vendors. I think uBlocks has also the Sarah series. They can do this as well. So now, if that was challenging even for the internet service provider to have a, let's say, antenna, well, they can go one step higher and have in some of this network, like high level, like internet, like providers, like in aggregation, and provide that, let's say, via PTP. Because most of the switches these days are capable to do hardware timestamping, because simply you have, let's say, a POP that will have a GPS receiver, and then from there, again, this is not only a GPS receiver, you can have the GPS, perhaps it's much better, especially when you go at such point that you're serving a lot of, let's say, users. You also put your atomic clock there and so on. And then from there, you provide time to the internet service provider that provides the time to your router, that provides to your computer, and so on, like the whole hierarchy basically is taken care of. So, and finally, let's say, on the cloud, if nothing is, like none of them, they want to budge, you put it on the cloud, where the cloud you have the time, and then via the cloud, you try to provide basically to all these systems. But now let's shift the focus inside the cloud. And by cloud, I mean in a data center. So you're familiar, hopefully, with a time card. So a time card basically is when you don't have those connections, and GPS is your only way to get in, time card, and I have here two on me. After the presentation, you guys can come and see it. Yeah, no, if you can get it, it's the second thing. So on the time card, you can put one or two GPS receivers. You can have actually one GPS receiver, and the other one can be like 5G, or you can have like a YY module. If Satoshi finishes it, so Satoshi. And then you have an onboard atomic clock that you can have an atomic clock, or you can have let's say an OCXO or TCXO depending. And then from there you have basically the same. We're calling it the open time server. Yeah. So yeah. So this is a time card. I think you've seen it before. So feel free to come over and see it later. I'll keep it here on the table. So from the open time server to the rest of the data center, we go with PTP. And now you get to all the machines with PTP again. You get to the NIC of the machines. There is still the challenge to get to the system and operating system, and it's already spoiled PTM. So these are the three domains where synchronization happens. And it's very similar to when you go outside the data center all the way to the end user. The difference is like over there, ISP and POP and like all of these, like router, all of these things are. But again, in a data center is much simpler because all of them are like homogeneous, and they're all like the entire data center is connected via either fiber or copper, so it's not wireless. So a little bit more about the open time server that time card sits in it. Basically, we wanted to have precision time synchronization in our data centers, and all the solutions in the market were not capable to do what we were looking for, because we wanted to have millions of devices in sync, while the state of the art was devices that they can do synchronization to maximum, let's say 5,000. And so also we wanted to have the provisioning of the software in our control. So we decided to open this box and basically have all these pieces under our control, where you take everything off the shelf, like components off the shelf, a NIC, or on software, and all that was missing, that was not there, was time card. And so in the beginning, it was just an idea, but now after 3 years, there are multiple vendors making it, combining it with their NIC, and it's just amazing to look like an idea basically turning to something like so widely adopted. So here's Mike, one of my colleagues. Like he, from day one, he's been always spinning the PCBs and making sure everything works on the first try. And again, this is like a miniaturized version of time card. That's like a PCIe if you want to put it on a laptop or something. And we're hoping we get this further, smaller and smaller, and we'll see in further slides what the plan is. So look at the time card. You have, as I said, you have the atomic clock, you have PTM coming up as well on the time card. So it means like from the time card, you can go straight to the CPU, synchronize the whole like chain. Or you can have time basically on the time card back by the atomic clock and so on. Now you feed the time back on air with YY to the rest of the systems in the vicinity that they don't have access to GPS for various reasons. Like, I mean, the most important one is like if you want to have GPS, then you need to have the antenna connection and indoor, like it defies the whole purpose why you have a mobile device. Like it's not mobile anymore. So you want to squeeze all these components, let's say, on that M.2 form factor. This is almost like basically correct size what they are sitting, and that you can see, like, okay, just the GPS module, of course, yeah, you can take this, you don't have to get the whole board. The antenna itself with the connection, that's really, I would say, the biggest showstopper. And CSACs, which I don't know why we call them chip scale, but here is a work from Motoaki, which is telling us that this is just like I don't know why it's called chip scale, but so I think because of this terminology, we had to come up with a new terminology, chip level. So chip scale and now chip level. So anyway, so hopefully this will lead into like having a component like this small and having the mascot happy. So we can squeeze this component straight on the module and we can have basically the atomic clock working there. But there is also another problem here, right? You solve this problem, you have a bigger problem. This and this. And here is where we think YY can help. And with YY, basically all of this can move somewhere else. Or let's say in case of what you guys are trying to do in Tokyo, you put it on the broadband tower and then everything, like in the vicinity, can actually receive this. And you're bringing out the precision time to the module, and then hopefully the chip level atomic clock is sitting there as well, so you can have the synchronization right in the system there. And here is a prototype, thanks to Nobu and Satoshi for this module, where now here is one time card with a GPS receiver antenna, not shown. So this time card is synchronizing these atomic clock. And then instead of, like, again, using wire or something like, again, sort of Ethernet, the synchronization goes via this wire over YY to this other module. And now, basically, this YY module is now receiving the PPS from this first time card from the atomic clock. And then from here, the PPS output goes to this atomic clock, and this time card, and you see, there is no GNSS receiver on this one anymore. And now this one is using basically the signal that comes from the YY and then synchronizes this atomic clock. So this work is still, like, we are doing more experiments and so on, and then it's going to be fully published in ISPCS in September. So all in all, when you do this, you synchronize the CPUs. So like, as I said, I will hop back and forth between why and how. This was like how, right? So let's go all the way to why. We have a lot of physics people here. They will probably get very mad at me. But I like to call, when you synchronize like these timers, pseudo-entangled. Because now, if you are simultaneously capturing the value of these two timers that are in sync with all these methods, you should get the same value. So they are within the uncertainty, the calculated window of uncertainty, entangled. So now, what can you do with it? So some years ago, I posted this, that I said, that time we were literally here with NTP, and slowly things were getting better, and we were like basically walking through this, and like we were trying to solve some of these problems where with these distributed databases and so on. But as technology starts getting better and better and better, and then let's say PTP with more adoption and like more, let's say, better granularity in the timestamp and in the quanta, we started like moving really toward, let's say, single-digit nanosecond, and now with, let's say, white rabbit, we can look into going deep, like in sub nanosecond, picosecond world. So what can we do really with this? So here is another breakdown of, again, this is more of a why. Inside the system, which I mentioned, you can have like the synchronization, let's say, between GPU, NIC, CPU, all these different things. And then between machines, let's say, you can have like this correlation of events, which I will show you an example shortly. And also, there are more things, like, for example, you can do some alignment between machines. You can have inter-machine telemetry, like basically you're comparing different machines. Again, I have them all classified I'll show you in a moment. So, as I said, like you can go from the CPU to every other piece, let's say it's an ASIC, it's a GPU, whatever, or straight from the time card, you can go back there, or from the time card going to the NIC in terms of like the time server. So this is all possible, let's say, giving you like all this synchronization between the devices sitting on one machine. But now, in one machine, let's say, in a cluster of machines, associating events can be very valuable. So what do I mean by that? So for Linux users, like for example, like vMessage, right? So the events are timestamped based on the local timer that is on that machine. And often, like again, it's called clock monotone underline raw, or let's say clock underline boot time. This is a timer that when you turn on the machine, it starts from 0, keeps going on. And it's on purpose, this timer is selected rather than, let's say, a UTC timer, because when a UTC timer gets synchronized, and let's say, I don't know, with NTP or something, like there jumps, or they can go back and forth or things. You don't want to have that. You want to have the events monotonically like logged. This comes with a challenge, let's say, if you want to associate events between machines. Because now when you look at the, let's say, the timestamp that is for an event on one machine, you don't know how is this related to another machine. Why is this important? So, and why do we need to have this association? I will show you an example shortly after I show you another property called linearizability. So, linearizability is another property that also involves a network. So in linearizability, you're trying to have cause and effect in a, like basically a synthesized way, where if you have a packet leaving from, let's say, machine A going to machine B, and the packet is timestamped in machine A on the departure and timestamped on the arrival on machine B, and you compare the departure versus the arrival, you should always have the departure after, the arrival after departure. And let's say in this case, we have two machines, A and B, and this is like the passage of time, and there is a latency between them. Latency between the two machines in this example is 5 seconds. And there is a difference between the two machines. You can see, while machine A is at 30, machine B is at 32. So a packet departs from machine A, goes to machine B. And you can see, it departs at 30, but then when it arrives to machine B, 5 seconds later, because machine B is 2 seconds off, it will be 37. So machine B opens a packet, it sees this packet was departed at 30 and arrived at 37, so machine B thinks latency is 7 seconds. It's not real, but it's still fine. There's a cause and effect. Machine B sends a packet at 32 to machine A. When it arrives to machine A, remember machine A was at 30, 5 seconds later, it will be at 35. When machine A looks at the packet, it sees it was departed at 32, and it arrived at 35, so latency is 3. Still there is a discrepancy between the two, but cause and effect works. Now, let's say, you see, like realistically speaking, this is like overall the system thinks where things are. But let's say, in the case where the clock skewness is, let's see, what do I have here? Yeah, so the clock skewness between the machines is 7 seconds. So basically machine A, and this is like perceived, right? In reality, like they're sitting like this is a perceived thing, right? So machine, and the five latency is still there, right? So machine A sends 30, and machine B receives it at 42, and he thinks there's 12, like let's say, seconds difference. Still things work. But if machine B sends a packet to machine A, machine B sends it at 37. When it arrives to machine A, it will be like 35. The difference is -2, and this is where linearizability breaks. This is where, like, you want to make sure your clock is tighter, the clock skewness, the synchronization, tighter than the best latency. In protocols like NTP, this is literally reversed, because you are sending packets over latency. I mean, in fairness, you're looking for the variance of the latency, but still the variance is so large that you will have an issue with linearizability. So how we are solving it is very inefficient. Like basically we are adding on purpose an extra latency and synthetic latency. Let's say, for example, when packets arrive, we wait an extra 10 seconds no matter what. So in this case, we'll see it like 22, and in that case, we'll see it like 8. Like there's always a 10 second. But that, like the addition of that synthetic latency just bloats the operation. You're just slowing down everything. So in case of the usage of associating events, this is another interesting thing. In distributed AI training, for example, or this can be also applied in security, but let's say in distributed AI training, you have a distributed data set. Like you have, let's say, for example, like 3 billion pictures, and then you have 30 machines, and you give every machine 100 million pictures, and they're all trying to do the training for, let's say, some classifier, and you want to use that classifier later on in production. So one way to do it is you just give all the machines, every one of them, they have their, I mean, ideally is you have one big machine, you give all the pictures and you train it and you get the data. But in reality, you can't do this, so you have to work between the machines. So the first methodology is called distributed model parallelism. In distributed model parallelism, you give the pictures each to the corresponding machines, you do the training, then you look at which one is giving, is resulting to a better accuracy. You pick that one as a winner, you go forward. Problem with this method is you might end up with a local minima rather than the absolute minima. In order to fuse all of it and aim for an absolute minima, what you do is on every, let's say, epoch or every, like in the sections of the training, you compare, every machine compares with every other machine. And if that machine has the best accuracy, it will continue. And if this machine is presented with a better accuracy from other machines, it will take that and will continue with it. This works great if everyone is saying the truth. So what happens here is, if, let's say, for whatever reason, again, this corresponds to machines we're like all going through training, right? At some point, this machine, like showing in red, ends up with the data that is too good to be true, for whatever reason. Like there was, let's say, some very similar pictures all in the row or something, and then that accuracy for that training got overfit with that data. So this machine will find a very strong and unrealistic accuracy. And when it does the sharing with this machine, for example, this machine will say, oh, this is much better than what I had. So it will take that one. And then all of a sudden, all the machines in the pipeline, they will adopt to this wrong value, and the whole model goes forward and it cannot converge anymore because it was just one instance of overfitting somewhere, and it results the whole thing to crash. Now, if you want to debug this as an engineer, you have to go and look which one started it first. How would you do this if you don't have a common clock between all the machines? And when these things can tick maybe all the way to single-digit microseconds. So that is, again, where precision time can be very helpful, because now you associate those events, although they were running by different, boot time, because different machines, they can turn on, turn off, whatever, they have their own things, or even if they started even at the same time, they will go off. They don't have atomic clocks. They're just some crystal oscillators, temperature is changing, and so on. But if you have a way to do the precision time sync across all of them, you can now associate those events. So this is a synchronization problem. Another thing that you can solve for is a synchronization problem. Again, you know that you don't build, like when you build CPUs, they don't look all similar. You may have one that, like, do you ever wonder why there is i3, i5, i7, i9? Did you know they only make i9s? They only make i9 CPUs, but then in the process of manufacturing and like how, again, Gaussian distribution, you will have a processor was meant to have 8 cores, only 2 work. So that one, and then the speed is also much lower or something. They go through a process of binning, and that from that process of binning, you will end up with like basically giving different grades, and then the one that stays all the way until the end, that's the most expensive one, that's the most special one, that becomes, let's say, i9 or something. Again, this for it applies to all the CPU or everything, even oscillators. Like they manufacture oscillators, they go through a binning. This oscillator is very precise, so this one will basically get sold more expensive because, again, in that Gaussian distribution, this one is like, somewhere right in the middle. So now, that same heterogeneity from nature will apply to the runtime for machines. Today, when you buy a processors are optimized for the power, not for runtime. As a matter of fact, again, physics people know this better. Not even for the same element, 2 atoms will not act the same, right? And you try to trap one of them to get the highest precision for your atomic clock. So now, this is, like the same thing applies also in processors and like in cache memory, in DDR, like everything. So therefore, you have different runtimes, especially when you're waiting for one machine to complete, like when you have like these processes of like serial to parallel, parallel to serial, serial to parallel, and so on. So let's say in this case, in this example, machine D or machine A is doing a great job, but guess what? They have to wait for machine C every time. So now, this is inefficiency, and like in some tests we've done, we can see like you can have up to 30% even difference between them because it accumulates. Like you can have a machine that the CPU is bad with a bad RAM and the cache and everything and the buffer and everything, and just adding up, and that pipeline is just slower. So we really want to aim to harness basically this part. And how we can do it is perhaps with using the synchronization. Now you know the difference for completion for every one of those nodes, and you can introduce micro adjustments, so micro overclockings. So now the CPU has to run faster to make up for that difference. And again, maybe not eliminating, but minimizing, and that will definitely drive you more efficiency. And again, there is no free lunch. When you do that, you'll end up with more power consumption, but great. You solve the time with consuming more power. So to summarize the use cases for precision time sync, I will say we can break them in 2 buckets, the synchronization and the synchronization. And for each one of them, you have an active and a reactive approach. Let's say in the synchronization, an active approach is when I run the events at a specific time. So these are like basically like you sync basically like the execution. And also there was actually another interesting use case where we had machines that, let's say, doing training or something, and we needed like this AI training. There is a certain point in the training where you have maximum power consumption. Let's say, for example, there is some add that is going like across, or like some multiplication, depends. Like let's say multiplication, it consumes more, and then all the machines are like, they were all consuming at the same time because they were all in sync. In those cases, you actually introduce a desync. You want to spread that power consumption, let's say, because you don't want to trip the fuse or whatever. You want to have like you have to manage how to go between things. Interestingly, for desync, you need actually sync. So then deliberately you will throw the machines off so they don't consume that peak power consumption at the same time. And the reactive is basically now you measure latency, or you measure time, or like when something got executed, or like time intervals. And then in case of the synchronization, again, the active is that you calibrate the speed and you align runtime, again, to reduce the tail latencies. And then in the reactive is, again, you measure the heterogeneity and then, or like you can provide binning. Let's say, for example, in those use cases, I said like you can overclock certain machines or so on. Or in cases that you have, let's say, a lot of machines and then somehow the network is like symmetric or something, and let's say you want to use, let's say, a subset from those machines, you can pick the ones that are similar by having them binned. You pick, let's say, you want 5 out of, let's say, 30 machines. You know, these 5 are the closest, so I go with these 5, and then I leave the rest for other processes to come in and, let's say, I don't know, use, let's say, based on what the demand is for them. So, in conclusion, precision time sync, we believe, is the future and is a must. We no longer can just go with machines just, you know, co-located in a data center or something. We want to have a computer the size of the data center. And these things are a necessity, but still not enough. So timekeeping devices needs to be further miniaturized. Like, you want to call it chip scale, chip level, I don't know. In the end, it has to be small. So we need to figure it out. Wireless methods are a must because we are no longer bounded by sitting, you know, somewhere and plug the computer or something. Everything is mobile, and we cannot expect people to go outside to use GPS. So we need to have better wireless methods, and new hardware architectures are necessary to look at, like, now precision time sync is baked into the design. And also we need to rethink how, like, operating systems and distributed systems can harness, you know, the synchronization that we are providing to this. And all in all, new challenges coming up, and that's a lot of fun. Thank you very much.